Hello and welcome to this presentation. I'm McKenna Haney and I'm a PhD student in Dr. Chris Langdon's lab. And this presentation covers the research on the effects of acidified seawater on Pacific oyster larvae, which were derived from either stressed or non-stressed parents. And this research was conducted by myself, Chris Langdon, and others in the Langdon lab. And the support from House Bill 3114 supported my work on this project as part of my dissertation. We are from Oregon State University and are based at the Coastal Oregon Marine Experiment Station at the Hatfield Marine Science Center in Newport, Oregon. So first, I would like to introduce the Whiskey Creek Hatchery, which is one of only 4 major shellfish hatcheries on the Pacific coast that produces billions of seed or eyed larvae for oyster farmers on the Pacific coast and abroad. It is the only independent hatchery that serves the needs of most of the smaller oyster farmers. The other 3 hatcheries are integrated as part of larger oyster companies, and the production of seed is primarily focused on meeting these companies' needs. So Whiskey Creek Hatchery plays a really important role for smaller oyster farms. Now, Whiskey Creek Hatchery, along with the other West Coast hatcheries, have experienced periods of reduced seed production due to the effects of upwelled acidified seawater, which is particularly severe during the summer months, and this phenomenon is called upwelling. So, of the several ions involved in ocean carbonate chemistry, the aragonite saturation state appears to be the most important parameter of seawater that affects larval oyster production. And this figure shows how larval production at the Whiskey Creek Hatchery was affected by low aragonite saturation state of the incoming seawater during these upwelling summer periods. And West Coast hatcheries now monitor and buffer their incoming seawater with chemical buffers to maintain optimal aragonite saturation states for larval seed production. Nonetheless, seed production is still not reliable, and there are periods when seed production is impacted by other undetermined factors. So we know that ocean acidification, or OA for short, is detrimental to marine life and aquaculture industries, but what is driving it? Well, ocean acidification is the ongoing pH decrease of Earth's oceans, primarily caused by the absorption of carbon dioxide gas from the atmosphere. And a simplified way to think about this relationship is as carbon dioxide increases in solution, the pH of the solution decreases or becomes more acidic. However, the underlying carbonate chemical reactions are slightly more complicated and arguably more important than considering pH alone. So previous work done by Waldbesser, Hales, Langdon, and others show that aragonite saturation state is the most important dissolved inorganic component for normal shell growth, and it will become a limiting factor decades before detrimental pH thresholds are met. Another study by Barton and others illustrates how dramatic some of these OA-induced physiological deformities can be in bivalve larvae. So what is aragonite? Well, it's a calcium carbonate polymorph that larval bivalves use almost exclusively to build their larval shells, making larvae extremely sensitive to undersaturated states during periods of rapid shell growth. And the aragonite saturation state, denoted by the symbol omega, can be calculated by multiplying the concentration of calcium by the concentration of carbonate ions, and then dividing that by the thermodynamic solubility of the product, which is calcium carbonate. So if the saturation state is under 1, it is considered undersaturated. If it is greater than 1, it is considered supersaturated. Now, larvae require a saturation state of about 1.14 for normal shell formation during the early larval developmental stages. So here are the objectives of our study, and the first step was to develop an experimental system that allowed us to control OA conditions during larval development. The second step was to make sure that conditions in this system supported larval development under specific OA conditions and to measure their effects on larval growth, survival, and setting success for our spat production. Lastly, we wanted to determine if the progeny from broodstock that had been OA stressed during the larval phase, then heat stressed as adults, performed better under OA conditions than progeny from non-stressed broodstock. This latter objective is important to address in that selection of stressed broodstock might accelerate the performance gains of oysters in hatcheries and farms. So now, having provided a background on OA and its impact on commercial oyster hatcheries, here is the outline of the subsequent sections of the presentation. First, we will discuss the development of the flow-through larvae culture systems, named the Huddle system. Then we'll show how stressed broodstock were selected. And lastly, we'll present the results and the conclusions of the study. So almost all previous experiments with marine larvae exposed to OA conditions have used static conditions in which there is no continuous exchange of seawater through the culture chambers. The lack of continuous exchange of seawater results in fluctuations in OA conditions in the static culture chambers. And you can see this denoted by the large red arrows on this graph. So these fluctuations are due to the respiration of bacteria and larvae, as well as microalgal photosynthesis, and make it difficult to maintain constant OA conditions. In contrast, flow-through culture systems, or systems that provide a continuous exchange of fresh seawater, provide more constant carbonate chemistry conditions with very small fluctuations. Additionally, most laboratories alter the carbonate chemistry based on pH measurements by additions of carbon dioxide gas. But pH probes are often not very accurate in their readings. So in our continuous flow-through system, we chose a two-stage carbonate chemistry manipulation system that involved coarse pH adjustment using well-calibrated pH probes, followed by a second stage of fine adjustment using a mass flow controller. So we added the OA control system to a previously existing flow-through system that had already been developed and tested at the Hatfield Marine Science Center by master's student Henry Fleener, and called it the Hatfield Ultra Density Larval System, or HUDLS for short. So some characteristics that make the HUDLS culture system unique are a larger chamber volume of 4.3 liters, the use of an anti-overflow device called the Brazilian T that prevents the loss of larvae if the HUDLS chamber's sieves become blocked. The chambers also have rounded bottoms, which allow for hatching of non-motile fertilized eggs under flow-through conditions. So here's a simplified diagram showing 3 HUDLS plumbed in series and a simplified version of our head tank reservoir system that provides seawater to the flow chambers. So this figure shows the two-stage carbon dioxide injection system design that was added onto the HUDLS flow-through system. So the first stage of carbon dioxide gas injection happens upstream of the HUDLS in a head tank and is controlled by a pH feedback communication loop with a computer. We used a GHL unit, which controls a solenoid valve on the carbon dioxide tank. And this served as our coarse OA adjustment and provided the largest pH change to our system. And for the fine pH adjustment, we bubbled in a precise mixture of carbon dioxide gas and carbon dioxide-free air at 1600 parts per million carbon dioxide to each OA-controlled HUDL chamber. This mix was maintained by Alicat mass gas flow controllers. And the control culture chambers were bubbled with unmodified air collected from outside the laboratory. So with this two-stage injection system, we were able to maintain steady acidified and normal pHs in HUDLS chambers containing oyster larvae and algae for multiple days. So this figure shows the sampling points where water samples were taken for the carbonate chemistry analysis. And these preserved samples were sent to the laboratory of Dr. Bert Hales at OSU for precise carbonate chemistry analysis. So the first parameter we looked at was PCO2, or the partial pressure of dissolved carbon dioxide. So on the y-axis, we have the seawater parameter of interest, and on the x-axis, we have the position in the system, starting with the incoming seawater, being split into the acidified head tank, the first normal or control head tank, and the second normal head tank. Then into the corresponding water lines to the Huddle's chambers, and then finally the Huddle outflows. And it's worth noting at the time of sampling, which was midsummer, upwelling had begun, and the incoming seawater was acidic with a pH around 7.5 for the first 8 days of the experiment. The pH of the unadjusted control seawater then had to be increased by bubbling with carbon dioxide-free air, while the acidified or OA treatment required much less pH adjustment with carbon dioxide bubbling via pH and mass flow controllers. So we also looked at total pH. Now, total pH scale considers all species that contribute to the acidity or alkalinity of a solution instead of only hydrogen ions. And this graph shows a similar but inverse trend to the PCO2 graph. And most importantly, we looked at aragonite saturation state, which again is that critical carbonate parameter determining shell formation. But the main takeaway from all three of these graphs is that after the second head tank position, seawater carbonate chemistry was not significantly changed after passing through the system. So now that we've covered the intro to OA, associated carbonate chemistry, the system infrastructure, and how we applied carbonate chemistry to the manipulation of the Huddle's flow-through system, we'll transition to the second part of this presentation, which describes how we selected our broodstock and studied the effects of OA on Pacific oyster larvae reared in the Huddle's system. So when it came to choosing broodstock, the G0 stressed parental oysters of the larvae tested in this OA experiment were pulled from a population of 75 combined crosses that had been subjected to OA stress as larvae and then subjected to heat stress as adults. The heat stress occurred when the mixed G0 population was exposed to high intertidal temperatures compared to subtidal or non-stressed conditions. The non-stressed parental broodstock were obtained from the same population as the stressed parental population, except the developing larvae and adults were reared under normal conditions. The oysters with the highest growth rates were selected by culling smaller oysters from flip containers that resorted the position of oysters every tidal cycle. Each container was originally stocked with about 2,000 spat. However, the final numbers of fastest growing surviving oysters was reduced to less than 300 at the end of this grow-out period. So samples of about 70 of the fastest growing oysters from the stressed G0 population and 70 from the control non-stressed population were genotyped, and then unrelated individual oysters from each group were used to produce the G1 generation, which were the larvae tested in the modified Huddle's system. So the spat from the G1 generation are currently being held at the Hatfield Marine Science Center for planting at a farm site later this May. So this figure shows the sequence of sampling of larvae and seawater from the Huddle system to determine larval survival, growth, and setting success, as well as seawater carbonate chemistry. So to start, we adjusted our water system to provide us with normal and acidified pHs. The next day, we spawned our broodstock and stocked embryos into the Huddles directly in an 8-and-8 arrangement. On days 1 and 10, we sampled the larvae and we did our carbonate chemistry samples. At day 14, we noticed pedivellagers were forming in the Huddles and setting began, and we also took our third and final carbonate chemistry sample. At day 20 post-fertilization, all setting had ended and all metamorphosed spat were moved into upwellers. At day 23, we sampled the spat that were stuck to the outsides of the upwellers, and day 35, we sampled the spat living inside the upwellers. So this figure shows the shell growth, or the average larval shell length, of larvae from different treatments at day 1 post-fertilization, a DPF, or day 10 post-fertilization for larvae, either retained on a 37 or 80 micron screen. Larval growth, or shell length, was adversely affected at all sample times by OA conditions, and this is regardless of their parentage. So here's another way of looking at that data. Larvae from non-stressed parents grew larger in normal seawater, which are represented by the solid green bars, at all measured larval stages than larvae from stressed parents, represented by the cross-hatched green bars. The OA conditions appeared to reduce this parental effect on larval growth. Furthermore, at days 10 post-fertilization, larvae retained on the 80 micron screen from stressed parents, the cross-hatched red bars, were significantly larger than larvae from non-stressed parents, represented by the red solid bars. Next, this graph shows the average larval retention per huddle vessel. Now, we use the term retention to describe the combined effects of mortality and loss of runt larvae when sieving larvae at each water change. So at all stages and treatments, there was a higher proportion of retained larvae from non-stressed parents, represented by the solid bars, than from stressed parents, represented by the cross-hatched bars. And these differences were statistically significant under OA conditions. And finally, this figure shows that the detrimental effects on OA, on the embryos and larvae in the huddles, also resulted in lower spat yields at 35 days post-fertilization. Further, the larvae from stressed parents yielded significantly fewer spat than larvae from non-stressed parents, regardless of rearing water condition. So in sum, we were able to achieve defined control of flow-through carbonate chemistry parameters, and this was possible with a two-stage gas injection design on a flow-through system. And the Huddles system is effective as the flow-through infrastructure for carbonate chemistry manipulation. It could also be effective for a wide variety of aquatic animals. And as for larval performance, the overall pattern is that both OA conditions and stressed parents resulted in lower larval retention and fewer spat. In other words, stressing the parents appeared to adversely affect larval and spat production of their progeny, suggesting that the stress selection approach used in this study is not effective in improving the breeding values of Pacific oyster broodstock. However, we cannot rule out the possibility that parental stress resulted in eggs of poor quality, example, lower lipid content, resulting in lower larval and spat production. So in other words, we cannot separate genetic from egg quality effects of parental stress on larval performance. Nonetheless, we were able to develop an effective system for testing the effects of OA on a wide range of planktonic organisms. So with that, we would like to thank the supporters of House Bill 3114 and the Oregon Coordinating Council on Ocean Acidification and Hypoxia for allocating funds to support this research and contribute to my PhD research. In addition, the research was supported by other state and federal agencies, including NOAA, the Pacific States Marine Fisheries Commission, and the Carlson College of Veterinary Medicine, Oregon State University. And numerous staff members and students of the aquaculture lab at the Hatfield Marine Science Center also contributed heavily to the study. So thank you for listening.